So far, we've learned how to find the location of an object by color and by using a method called background subtraction. However, the locations that we've found are still in units of pixels. We would really like to be able to find the location of an object not in units of pixels, but in physical units like centimeters. The reason that we want to do this is because when we build our manipulator, the units that we use to define the location of the end effector is also in physical distance units like centimeters. If we want to be able to send a command to the end effector to move to a position where the object is, we need to be able to tell the end effector to move to a position not in units of pixels, but in physical units like centimeters. In order to accomplish this, there are two steps we need to take. The first step is to convert units, pixels to centimeters. That step is the easier step. We already know how to convert units. If we have a number in units of pixels and we want it to be in units of centimeters, all we have to do is figure out a conversion factor that tells us how many pixels in the image are in 1 physical centimeter. The second step is a little bit more complicated. In that step, we need to do a conversion from the frame of the camera to the frame of our end effector. We're going to start by doing the first step, converting the units of pixels into units of centimeters. I'll show you how we do that. I have here the code that we ended with in the last video, which was finding the location of an object using background subtraction. For now, I'm going to take all of the lines of code, starting at the pause, all the way down to the end, and I'm going to comment all of these lines of code. This will allow us to just see a preview of the video. And I'm going to run this code. And here I got an error that you might get sometimes. This error, which says the device associated with device ID 2 is already in use. That means that you haven't closed your preview window. All you have to do when you get an error like that is find your preview window, close it, and then you can go ahead and run your code again. Okay, so here is our preview window. Remember, what we're trying to do is to find a conversion factor that tells us how many pixels are in a centimeter, or how many centimeters are in a pixel. Now, we already know the dimensions of this image. It has 640 pixels in the horizontal direction, and it has 480 pixels in the vertical direction. If I can figure out how many centimeters there are from left to right or from top to bottom, that will give me a conversion factor between pixels and centimeters. So the way I'm going to find this conversion factor is by placing a ruler in my field of view. I'm going to place the ruler in the field of view, and I need to do a little bit of moving this ruler around. I'm trying to line up the 0 mark with one side of the screen. Now note that the pixel to centimeter conversion that you get will depend upon how you've bent the camera, how far away or close it is to the board, so your number might not be the same as my number. I've lined it up pretty closely here, not exactly, but it's lined up almost exactly between 0 centimeters and 15 centimeters. So I'm going to go back into my code here, and I'm going to create a variable way up at the top. And I'm going to call this variable centimeters per pixel. And that value is going to be 15 centimeters divided by 640 pixels. Now, as I said, your number might be different than mine based upon how far away from the board you've placed your camera. You're just putting the number of centimeters in the horizontal field of view divided by the number of pixels that you have in the horizontal direction. Now, I'm going to go and uncomment the rest of this code. Let's do a conversion down here to convert the column and row location in units of pixels into units of centimeters. Let's create a variable called x location. I'd like the units of x location to be centimeters. The x location currently is indicated by our variable column location, but that's in units of pixels. So I'm going to take the value of column location and multiply that by our conversion factor, which we called centimeters per pixel. I'm going to leave the semicolon off of this so that it will print this value to the screen. Similarly, we'll calculate the y location from the row location. Row location is in units of pixels, so we'll convert it to centimeters by multiplying it by centimeters per pixel. Now, let's try it. The x is pretty close, so our x and y locations should be relatively close to the actual location of the nut. Let's take a look at what our numbers are and let's check how accurate they are. X location is 4.4. Let's take a look. The actual location of the nut in the x direction appears to be roughly 3.5. So this is off by about, or maybe not, maybe it's about 4. So this is off by about half a centimeter in the x direction. And let's check the y location. The y location is 7.2. It's about 7.25 centimeters. So now I'm going to try to measure its location from the top of the screen. Its actual location from the top of the screen is about 7.9 or so it's also off by about half a centimeter here, but still that's pretty good. Note that the 0, 0 location in your camera field of view is in the upper left hand corner. This is 0, 0, and the x direction is measured this way, like this. Trying to draw that in the, that's the x direction. And the positive y direction for your camera is over here. That's positive y. And this is our camera frame. Just like in the first unit of class, we had different frames, the base frame, the end effector frame, and a frame for each joint. We now also have a frame that is for the camera. And this is where the camera frame is, the upper left-hand corner, and pointing out in those directions. Go ahead and draw that frame on your board. Now, when we build a manipulator on this board, the base frame of the manipulator will probably not line up with the camera frame. Take a look at the way these 4 holes are in your camera frame. I'm going to erase some of these things here to give us a little more space to draw. If you would attach a servo to these 4 holes the way that we do when we're building our manipulator, you would probably find that the X and Y axes of your base frame would look something like this. This might be the X0 axis. And that might be the Y0 axis. Now, when we find the location of an object by using our centimeter to pixel conversion, the location that we're finding is in the camera frame. In other words, the Y location in centimeters is this distance here. And the X location that we find is this distance here. In order to be able to command our end effector to pick up this object, we need to know the location of this object not in the camera frame, but in the base frame. In other words, we want to know the X location here. And we want to know the Y location here. That is, we want to know the X and Y location of the object relative to the base frame of the manipulator, not relative to the camera frame. Do you remember something from our first unit of class that would help us to transform the location of a point in one frame into the location of a point in another frame? We can use a homogeneous transformation matrix to do this. Instead of finding the homogeneous transformation matrix from the base frame to the end effector frame, in this case, we need to find the homogeneous transformation matrix between the camera frame and the base frame of the end effector. As a reminder, we learned previously that if we know the homogeneous transformation matrix from the base frame to the end effector frame, we can multiply that matrix by a point in the end effector frame. And when we do that, that will tell us the location of that same point in the 0 frame. Let's use this analogy to help us find the location of our nut in the base frame instead of the camera frame. We could find the position of the nut in the 0 frame by first finding the homogeneous transformation matrix from the 0 frame to the camera frame. Then we could multiply this by a point in the camera frame, which we've just found in our code, and this will tell us where the object is located in the base frame. Let's try it. We find the homogeneous transformation matrix the same way we did previously. We'll find a rotation from the 0 frame to the camera frame, and then we want to find a displacement from the 0 frame to the camera frame, and then we'll fill in zeros and a 1. Let's find the rotation first. Looking at our live image, can we figure out how to rotate the 0 frame in order to get it to match the camera frame? In order to figure this out, the first thing you have to do is figure out the direction of the z-axis. The z-axis in the camera frame is pointing down. You can find this out by using the right-hand rule. If we put our fingers in the X direction and the palm of our hand in the Y direction, our thumb will be pointing down. In contrast, for the base frame, the Z-axis is pointing up. Let's start by trying to get one of the axes of the zero frame to match one of the axes in the camera frame. We could do this by rotating the X0 axis to match the XC axis. That would be a rotation around Z0, which is pointing up. I'm going to draw this rotation on my board. Here's the direction of XC. It's perfectly horizontal. If we would rotate X0 like this, this would be around the Z0 axis, which is shown by my marker here. We can estimate how many degrees this is by using a protractor. In my case, this angle is about 60 degrees. So this is a rotation of 60 degrees around Z. Let's add that to our rotation matrix. I'm going to get this standard matrix for a rotation around Z, and I'm going to plug in 60 degrees. Now that my X-axis matches, all I have to do is rotate the frame to get Y, which will now be pointing straight up, to flip all the way over and match this Y here. That will be a rotation around X 180 degrees in the positive direction. So I'll add this rotation to my matrix by going to get the standard rotation around X and plugging in 180. Now, I'm not going to go through the step of calculating this out because I don't have any variable angles here, and I'm going to be adding this to my MATLAB code anyways. Let's go to the MATLAB code and put this in. Let's create a variable called R from 0 to C, the camera frame. This is equal to the cosine, and then I'll put D because I'm going to give these angles in degrees, of 60, then the negative sine of 60, and this will be multiplied by my other matrix, Now before I move on, I'm going to test this. I'll remove the nut from the field of view. Make sure my figure windows are closed, and then run this code. I don't get any errors, and the rotation matrix is printed out for me. So I'm going to continue. Now that we have the rotation matrix, we still need one other part. We need to get the part of the displacement from frame 0 to the camera frame. Finding the displacement vector from the 0 frame to the camera frame is kind of tricky. I'm going to try and show you here how we do that. our goal is to find the displacement from this point to this point along the x0 direction and along the y0 direction. The reason why this is tricky to show in the camera is because the camera doesn't right now show the total distance that we have to measure. So let me see if I can show you the y example first, and then we'll do the x example, which is more difficult. So I'm going to line up the ruler so that 0 is at the center, and I'm trying to get the ruler to lie right along the y0 axis. And I need to measure down from the location of here to the location of here in this axis. So I'm going to come down and draw a perpendicular line, which I'm showing here with my marker, from the center to this ruler. So in the y direction, the displacement from 0 to the camera frame is about -4. I'm going to take note of that over here. In the y direction, the displacement is about -4. Let's see if we can get the displacement in the x direction. I'll line up the ruler along the x0 direction, and I'll get the 0 point right in the center. However, the point that I need to measure to is currently off screen. What I'm measuring is shown by I'm trying to get my marker in the field of view here, is right like this. I'm going to place my marker parallel to the Y frame, and then I'm going to slide the marker back until it measures from the center of the camera frame, shown up here in the corner, over to where it meets my ruler. And that number is about 7 1/4. So I'm going to record the x displacement as being about -7.25. Now the z displacement between these two frames is easy. It's 0 because the z position is the board, and both of the centers of these frames are on the board. So now I'm going to go back to my code, and I'm going to put in the displacement. D from 0 to c will be equal to -7.25 in the x direction, -4.0 in the y direction, and 0 in the z direction. Now I can use this to build my homogeneous transformation matrix. The complete H03, or H0C that is equal to the rotation part, followed by the displacement part, followed by 3 zeros and a 1. Lastly, we can use this homogeneous transformation matrix to convert the location of a point in the camera frame to a location of the point in the 0 frame. We'll call the location in the 0 frame P0. This is equal to H from 0 to C times the position of the object in the camera frame, which we already found back here, calling it X location and Y location. X location, Y location, the Z location is 0, and then we always need to put a 1 at the end in order to make the dimensions match the dimensions of the homogeneous transformation matrix. So let's test this. I'm going to make sure that my field of view of the camera is cleared so we can get a nice background image. Then we'll run the code. When prompted, I'm going to slide the little nut into our test location and click OK. The location of the nut is not found exactly, but we're approximating in a number of ways. So let's check and see if our numbers are at least close. P0 is telling us the location of the nut in the 0 frame. It says that the location is almost -1 centimeter in the X direction. Let's check and see if that's true. I'll line up my ruler with the X direction, and we'll see that the actual displacement is about 1.5. So that's off a little bit, but it's pretty close for our approximations. And our number here is telling us that the Y displacement is about -2. Let's see how well we did there. The actual Y displacement is almost -3. It's about 2.5. So we're also off a bit there. Note that I am still using a grayscale image to find the location of my object rather than converting to a black and white image like we did in the last lab. And so my red X is off of the location of the nut. If you are using the thresholding approach to convert the image to black and white, you can probably get quite a bit more accurate than this.